Hello students, welcome back to our physics class. Today I am going to explain you Gauss law in static electricity. This is an expression which was derived by Gauss to find the electric field for a closed surfaces. If you consider a charged conductor of positive or negative charge, it considers the electric field around it, and the surface area of the conductor is of two types. One, open surface, and the second one is closed surface. If you consider a long straight conductor just like a wire, and this is the wire, and two ends of the wire are open, and the surface of the conductor is called open surface. And if you consider a substance like a cylinder, sphere, metaplate, or a disc, then we can calculate the surface area, and the charge can be distributed over the surface, and we can calculate the volume, and the charge is distributed within the volume of the substance. So for closed surfaces like cylinder and sphere, other substances, sorry, other conductors, we have to calculate the electric field at any point within the field. Intensity of electric field is calculated by Gauss law. We know that the electric intensity of the field is E equals to 1 upon 4 pi epsilon naught Q by R square. For closed surfaces, how can we write the expression for electric field? How to derive the electric field? At any point on the surface, outside the surface, and within the surface, inside the surface. So we use Gauss law to find the electric field for those substances. And this Gauss law is derived in two ways, using the integrations and using the differentiation. So if you derive Gauss law using integration, this is called integral form. And differential form, there we use the differentiation of electric field. And the electric field is expressed as the divergence, nothing but del dot. Then that is called differential form. In this class, I am going to explain you integral form of Gauss law here. And remember, electric field, intensity of electric field is a vector. Intensity of electric field is calculated over the given surface area, as intensity is a vector and the given surface area is also a vector field. So we have the two vectors here. One is the electric field and the second one is the surface area where we calculate the electric field. So we use the differentiation and the integration of vectors. We don't use the normal or ordinary differentiation and integration. We use the surface integration, volume integration, and a linear integration. Of vectors, we use Gauss divergence theorem in this topic. So now let us start. How to derive Gauss law and what is Gauss law here. So this Gauss law, it is for electric field as I said. So this Gauss law is derived using the electric flux formula here. So we have the expression for electric field. Electric field at any point within the electric a given positive or a negative charged field. Intensity of electric field is 1 upon 4 pi epsilon naught q by r square. So if you consider a charge, either positive charge or a negative charge, the electric field is developed around that. Within the field, at any point, so if you consider any point here within the field, and the distance between the point and the charge is r. At this point, intensity of the electric field is E. This is due to the point charge. If the charge is distributed over the surface area R within the volume, then how to calculate? So this formula is for a point charge. And how to calculate E if you consider a charged conductor like a cylinder and sphere, and the charge is distributed on the surface or within the volume for that. So for that we use this equation here, and phi equals to electric flux here, where total number of lines passing through the electric field. So this is phi, electric flux, and phi by A, flux density, total number of lines passing through unit area, flux density, numerically equals to intensity of electric field. And cross multiplying this, we have this formula phi is equals to E dot A, total surface area of the given electric field. Now we divide this surface area into small and equal elements. Each element has the surface area ds. ds is the small surface area, and this ds, it is integrated over the surface. So this is the integration of ds, surface integration. This is the integration over the surface, closed surface. Then instead of A, we calculate surface integral E dot ds. Then electric flux will be surface integral E dot ds. We use this formula for calculating intensity of electric field and to derive the Gauss law also here. So what is Gauss law? And what's the statement? What does it state? Gauss law. So here we have the statement of Gauss law. Here we have considered a closed surface having the total surface area A, and we distribute the charge on the surface area. Remember, the charge is distributed only on outer surface area only. Only on outer surface area the charge is distributed. So the influence of the charge is only from outside the surface only. There is no influence of the charge inside the surface. Then, if you consider an electric field or a closed surface like this, and charge is distributed uniformly here, either it is plus or minus q. If it is a positive charge, then the field is outward. If it is a negative charge, the field is inward here. So the field will be inward at any point. So for this closed surface, total charge is Q distributed over the surface, and electric flux, total number of lines passing through the electric field. So electric field is developed here around this surface. Around the surface, electric field is developed. Within the electric field, at any point, total number of lines passing through the electric field, that is electric flux, which is equal to surface integral of E dot ds, and this equals to q upon epsilon naught. It means 1 by epsilon times the charge distributed over the surface. So total electric flux, which is passing through the given electric field, which is expressed as surface integral of E dot ds, as we have discussed just before a moment. This is equal to here q by epsilon naught. So this is 1 by epsilon naught times charge distributed. So this is the statement of Gauss law in integral form because we have considered this integration, surface integral of E dot ds. Q is the total charge, epsilon naught, permittivity of free space. And if you place this conductor in a medium other than free space, vacuum, any other medium, then this epsilon naught is replaced by epsilon, permittivity of the medium here. So this is Gauss law statement here. So we have to prove, verify this Gauss law. That is total electric flux passing through the electric field in a closed surface given area is 1 by epsilon naught times the charge distributed over the surface here. So to prove Gauss law or to verify Gauss law here we have to consider a small sorry, a closed surface here. Now I consider a closed surface. So this is the closed surface. And total surface area, this is A. Total surface area is A of the given conductor. Now I divide this total surface area into small equal surfaces, just like a graph paper. And each surface, small surface, we denote with ds. This is the small surface here. And to draw the direction of this surface, I said this surface is also a vector because we are calculating electric field within the surface. So to draw the direction of this vector surface, we have to draw a normal here. So this is the normal drawn to the surface here, this one. And an amount of charge is distributed over the surface here, over the surface, and an amount of the charge is distributed here. And so electric field is developed around the conductor. Then direction of the electric field. Here we have the direction of the electric field, and this direction of the electric field is um, this one. This is electric field here, and this is the angle between the two vectors. That is the vector E electric field and ds small area. I denote this angle with theta. Theta is the electric field, angle between the electric field and the normal drawn to ds here. Say closure surface is considered and we have distributed a charge q uniformly over the surface and electric field is developed around the surface and we have divided the total surface into small and equal parts and each part is having an area ds and this ds it is in the direction normal drawn to the ds and E is the electric field at the area ds where we have drawn the normal. An angle between the normal and the E is theta here. So this is about the concept. What what to be considered here. So the next one is here. We have to consider the electric field here and total surface area. So before going to electric field, here we have total surface area in terms of intensity of electric field. In terms of integration, here we have A equals to surface integration ds, where ds is the small area. So total surface area is equal to the closed surface integration of ds. So we consider this here. And then we have E, formula for intensity of electric field. Intensity of electric field is 1 upon 4 pi epsilon naught q by r square, where q is the charge distributed, r is the point where we have to calculate electric field here. and theta is the normal, theta is the angle between the normal drawn to the ds and E here. Now, coming to the relation here, what we have discussed before starting this topic, electric flux phi equals to integral E dot ds, surface integral E dot ds. So this is electric flux. Now this is in the form of the surface integral A dot B. AB are two vectors here. This will be AB cos theta. So we have this formula, that is a vector product, scalar product of two vectors A dot B dot product AB cos theta, that we have used here. So AB cos theta, this is. And here we have substituted E value. Here we have substituted E value here, 1 upon 4 pi epsilon naught, this one, and then q by r square ds cos theta. Is it clear? So see, just we have taken the dot product of E and ds, E dot ds equals to E ds cos theta, and we have substituted the value of E, 1 by 4 pi epsilon naught q by r square multiplied by ds cos theta. Then what's the next step? Very simple. We have to take it away, 1 upon 4 pi epsilon naught and q here. So we will do that. So phi value is here. So left hand side is the same, surface integral E dot ds, and right hand side here a small modification. Here this is a q by 4 pi epsilon naught is taken out, and within the integration we have here surface integral of 1 by r square ds cos theta. What is this here? So this 1 by r square, this value 1 by r square ds cos theta. This value equals to a small angle, which is solid angle, which is produced at the center of the given conductor, solid conductor, by this area ds. This is the solid angle produced by ds at the center of the given conductor. It's a solid angle because we have taken the solid sphere, solid cylinder like that. So angles are two types. One is the plane angle and another is the solid angle. For closed surfaces like a cylinder and a solid, the angle produced at the center is solid angle. We can calculate that, which is in steradians, but plane angle, which is at the center of the circle, which is calculated in radians. So this is the solid angle, 1 by r square ds cos theta. But the solid angle is the angle produced by small area ds. We denote this with only this part. We denote this part with d omega. This one. This is d omega. What is this with d omega? Small solid angle here. And then this will be surface integral E dot ds equals to q by 4 pi epsilon naught, and instead of 1 by r square ds cos phi, we have surface integral d omega. And surface integral d omega is the total angle, solid angle. The total net solid angle produced at the center of the given solid conductor by total surface area. Then this value equals to 4 pi. Total solid angle, which is subtended at the center of the given solid conductor by this total surface area, is 4 pi. So we have substituted this for this instead of this value 4 pi. So then here the equation will be, here we have the equation here, left hand side is E dot ds, and outside the integration already q by 4 pi epsilon naught. So instead of integral d omega, here this value is d omega. and this 4 pi, it is the integration of d omega, and 4 pi is cancelled here. So you will have this one, surface integral E dot ds equals to q by epsilon naught. So nothing but the integral form of Gauss law. The total electric flux equals to q by epsilon naught, 1 by epsilon naught times the charge distributed over the surface here. This is very simple. Just you have to take only two steps. One is a surface integral E dot ds equals to q by epsilon naught. This one. So just take left hand side equation. E dot ds, E ds cos theta. Substitute the value 1 by 4 pi epsilon naught q by r square surface integral ds dot this is. So if you remove the dot, it will be cos theta, and surface integral 1 by r square ds cos theta is d omega small solid angle subtended at the center of the solid conductor by ds, and over integration it is 4 pi. 4 pi get cancelled. You will have integral E dot ds equals to q by epsilon naught. So this is about Gauss law. Surface integral E dot equals to q by epsilon. From this equation only we derive differential form also. I'll explain you in the next class.